recording. Yes, it is. All right, welcome back. Welcome back from the fall break. And our exam 2 is approaching next week. On Tuesday, I'll collect homework number 2, and I'll give you a handout for exam number 2, which is take home. So you have 2 days to complete it and bring it to me on Thursday of next week. All right. So we started talking about second order ODEs last time around, and we talked about the fact that second order ODEs, when they're linear, we can solve them. We can find an auxiliary problem, solve for the roots, take those roots, and depending on the nature of those roots, then the solution will have a form, whether it's trigonometric, exponential, or a combination of the two. Then we talked about, well, how about we keep them linear, but we make them, variable coefficient. Then we talked about the fact that these actually lack a general solution. There's a specific kind of second order variable coefficient equation, linear equation, that's called we went over it, the Euler equation, the Euler-Cauchy equation, that has a specific solution that we worked out. But it's essentially the only variable coefficient second order linear equation that has a solution that is that simple. All the other ones require special treatment and usually leading to a much cumbersome type of process of getting to the answer. Now this solution process that we can construct is usually based on a series approximation. So we're going to start from the premise that we can expect the solution to be a series summation of something, of some terms, which can be either polynomial or trigonometric or whatever. And then somehow we're going to try to fix the coefficients of these infinite series and collapse them into two coefficients. Because remember, a second order equation, we can expect that the general solution of a second order equation will lead to two integration coefficients, right? So we have two functions, two coefficients, and those two coefficients should be actually fixed with boundary conditions or initial conditions. So let's look at that. This is Math and Modeling Methods, Lecture 15. Lecture number 15. So we're going to talk about series solutions method for second order. We're still talking about linear variable coefficient ordinary differential equations. Okay, so let's assume again that we're given this equation and it's written in this particular form. So we're looking for a function y of x. So this is a boundary value problem. It's a variable y, which can mean temperature, which can mean pressure, which can mean voltage, or anything that's a function of space, x being the space, plus q of x, y of x, is equal to 0. And again, let's keep it homogeneous for now. We know that the non-homogeneous portion we can do through indeterminate coefficients, following the steps that we went over last class. Okay, so let's assume that px and qx, which are precisely the variable coefficients, those are coefficients multiplying the first derivatives and the zeroth derivative. Let's assume that they are non-singular continuous functions. So non-singular continuous functions of x, obviously. and try a solution y of x in terms of Taylor series such that we're going to let y of x be equal to the summation from we're going to use n, yes, n equals 0 to infinity of the nth derivative of y evaluated at point x0. So we're going to call this d, and this n go in here actually. The nth derivative of y evaluated at x0 times x minus x0 to the power of n. Okay? The nth derivative of y, where the zero derivative at n equals 0 is a 0, that's just a function of y. And by the way, I forgot, divided by n factorial. Okay, that is a standard Taylor series. Which, if you recall, a Taylor series basically says that we can expand any function we want, as long as that function is continuous and non-singular, in terms of an infinite series of polynomials. Okay? That's all the Taylor series is saying. We pick an expansion point x0, and that function y, whatever it is, I give you a function y, let's say that we already know it. We can expand that function, basically come up with an analogous to that function, in terms of a polynomial series from 0th order to nth order to infinite order. That just looks like this. And these are the coefficients of those polynomials. The nth derivative of that function evaluated at the expansion point. This expansion point is arbitrary, but it makes a big difference of what point we use, because the radius of convergence of a Taylor series is associated with that point of expansion. Okay? The closer you are to the point of expansion, the more bound to converge the Taylor series is. Okay? The more bound to converge this polynomial approximation of that function. Okay? This works well when we know the function. If I give you a function, sine, a cosine, an exponential, you can expand it in Taylor series and end up with a polynomial approximation of that particular function. Now we're assuming that we are going to use a Taylor series for a function that we don't know. We're trying to find that function, and we're going to start from here. Okay? So, since we don't know the function, y, that's what we're trying to find, we basically cannot calculate its derivatives and evaluate those derivatives at the point x0. So, since y of x is unknown, its derivatives, that's dn y dx of n, may not be directly calculated. Therefore, express the series as, well, y of x is just simply the summation from n equals 0 to infinity Cn times x minus x0 to the power of n. Okay, some coefficient Cn, and manipulate it to end at a general solution expression that looks like this. Y of x is equal to C0 times some f of x plus C1 times some g of x. Okay? So somehow we're going to take that series that is infinite, and somehow we're going to be able to split it into two and end up with two coefficients only, because we can only afford to have two integration constants, not an infinite number, as we're showing here. Okay, here we're showing an infinite number of integrating constants, or an infinite number of constants to be determined. We cannot determine an infinite number of constants because we only have two boundary conditions. So the most that we can have is two. So somehow we're going to take this to this. Okay? So let's see how we do this. Is that clear? The process that we're going to follow? All right. Yes? All right. So let's do this with an example. Solve d second y of x dx squared plus y of x is equal to 0. All right? Well, this one doesn't look like a variable coefficient, ODE. It is a constant coefficient, ODE, where p of x is equal to 0 and q of x is equal to 1, right? If we compare it to the form that we expressed, or that we showed above. So this is a constant coefficient ODE. Do we know the solution to this ODE? Think about it. This is a linear ODE, so we can use the auxiliary problem and find the roots. What are the roots of this equation? M1 and M2? What are the roots of this equation? Minus b, plus minus square root of b squared minus 4ac.
By 2a.
Huh?
By, like, over 2a. Like,
Yeah.
divided by 2a.
Divided by 2a, so what do we end up with? b is equal to 0, a is equal to 1, c is equal to 1,
Plus minus 1.
plus and minus square root of minus 1. Okay? It's negative, the argument is negative. So we end up with plus minus square root of minus 1. So the roots are plus and minus I, right? So when you have imaginary, what do you get? Sines and cosines, right? So you get sine of x, cosine of x. So you get C0 times the cosine of x plus C1 times the sine of x. That's the solution of that equation. You can try it, right? If you plug in sine of x, does it cancel out? What is the second derivative of the sine of x?
Negative sign.
This negative sine plus sine cancels out, is equal to 0. What is the second derivative of the cosine of x?
Negative cosine.
Negative cosine plus a cosine cancels out. So that's the solution, sine, cosine. Well, let's try this series approach and see if we can get to the same. We should, whatever method we use, we should end up with the same solution. That's a unique solution, right? A linear equation shouldn't have different kinds of solutions. So we somehow should end up with the same. So we're going to so note, p of x is equal to 0, q of x is equal to 1. Alright, so we're going to let the solution y of x be equal to the summation from n equals 0 to infinity of Cn x minus x0 to the power of n. It's an infinite series, an infinite Taylor series. So what is the first derivative of these? The summation from n equal 1 to infinity of Cn times n times x0 to n minus 1. Is that clear? And is it clear when we start the series at 1 instead of at 0? The first polynomial is of order 0, well, that goes away. Right? The derivative of a constant is 0. And hence the second derivative of these with respect to x squared is then the summation from n equal 2 to infinity of Cn times n minus 1, x minus x0, n minus 2. Plug back into ODE. So we're going to take this and plug into ODE, and we end up with, well, this one is a summation from n equal 2 to infinity Cn n minus 1, x minus x0, n minus 2, plus y, which is is equal to the summation from n equals 0 to infinity of Cn x minus x0, and that's equal to 0. Alright? So now let's try to make those two series compatible. And to make them compatible, we're going to try to start them both at 0. Right? So that we can combine them into a single series. So we're going to try to start them both at 0. So in order to start them at 0, we're going to do a shift of variable. So shift index of first summation, so that m is equal to n minus 2, or n is equal to m plus 2. So we're going to switch n to m. So when n is equal to 2, m is equal to 0, right? So then what we have is m equals 0 to infinity. Well, the infinity doesn't need to change to infinity minus 2, because infinity minus 2 is infinity. So this would be c m plus 2. This will be m plus 2. This will be m plus 2 minus 1. And this will be x0 to the m plus 2 minus 2. And the second summation stays the same. Alright? So now I can take m and switch it back to n. Switch back from m to n. So I'm just going to call it n. This is going to be Cn plus 2. This is going to be n plus 2. This is going to be n plus 1. And this is going to be x minus x0. And this is going to be n plus n equals 0 to infinity of Cn x minus x0 n equals 0. Alright, now we have two summations that use exactly the same index that start at 0. And now we can combine them. So now we combining. We have the summation from n equals 0 to infinity of Cn plus 2, n plus 2, n plus 1, plus Cn x minus x0 to the power of n is equal to 0. Alright, so it looks like we're getting somewhere. Now, bless you, there's a product here of coefficients times polynomial terms, okay? And in order to arrive at a non-trivial solution, this needs to be equal to 0, not this. See, the product of these times this is equal to 0. So either this is 0 or this is 0. Okay? This cannot be 0 because that will make the whole solution equal to 0. That's a trivial solution. It's a valid solution, but it's trivial. Okay? So in order to make this a non-trivial solution, the only choice is for these to be 0. So we're going to make that 0. For a non-trivial solution, Cn plus 2, n plus 2, n plus 1, plus Cn needs to be equal to 0. Which means that Cn plus 2 divided by Cn is equal to minus 1 divided by n plus 2, n plus 1. And this here is called the recurrence relation. Any idea how that's going to help us? right? Well, we suggested this to be the solution. This has infinite number of constants to be determined, right? We cannot afford that. We only need 2. We can only afford 2. This recurrence relationship is giving us a correlation between every 2 coefficients. So if I know C1, I know C3, and I know C5, and I know C7, right? If I know C1, if n is equal to 1, and somehow I know C1, that means that I know C3. I just need to replace this with 1, 1, and 1. And if I know C3, then I know C5, right? And if I know C5, I know C7. So all I need to know is one of them, C1, to be able to know the next 2 and the next 2 and the next 2. How about if I know C0? If I know C0, that means that I know C2. And if I know C2, that means that I know C4. And so on and so forth, right? So the only thing I need to know is C1 and C0. As long as I know C1 and C0, I have a relationship that will give me C2, C3, C4, C5, all the way to C infinity. Okay? So those are no longer unknowns. Those are dependent on C0 and C1. Okay? So this means that we only need to know C0 and C1, and the rest of the coefficients will depend on these 2. That is, for n equals 0, we have C2 over C0 is equal to minus 1/2. Right? If I replace n with 0. If n equal 2, then C4 over C2 is equal to minus 112. Right? And therefore, I can say that C4 over C0 is equal to 1/24. Right? Just replace that. So if n equals 4, C6 over C4 is equal to minus 1/30. Therefore, C6 over C0 is equal to minus 1 over 720. And so on and so forth. Similarly, for n equal 1, C3 over C1 is equal to minus 1/6. For n equal 3, C5 over C3 is equal to, just plug in the value of n there, you end up with minus 120, which means that C5 over C1 will be equal to minus, or plus, I'm sorry, 1 over 120. n equal 5, C7 over C5 is equal to minus 1 over what? When n is equal to 5, we get 7 times 6, 42. Negative. And therefore, C7 over C1 is equal to minus 1 over 5,040. Are you following? All right, and we can continue. So we know that all the odds are related to each other, and all the evens are related to each other. So this means, therefore, y of x, which is equal to the summation from n equals 0 to infinity of Cn x minus x0 to the power of n, could be expressed as C0 times f of x plus C1 times g of x. And if we look at this this will be, let's separate the odds from the even here in the summation, and we'll have C0 plus C2 times x minus x0 to the power of 2 plus C4 times x minus x0 to the power of 4 plus C6 times x minus x0 to the power of 6, so on and so forth. Plus C1 times x minus x0 to the power of 1 plus C3 times x minus x0 to the power of 3 plus C5 times x minus x0 to the power of 5 plus, well, all the rest. Again, I can take C0 as a common factor and C1 as a common factor here. Y of x will be C0, 1 plus C2 over C0, x minus x0, plus C4 over C0, x minus x0, plus C6 over C0, x minus x0, plus C1 I can take as a common factor, that's x minus x0, plus C3 over C1, x minus x0 cubed, plus C5 over C1, x minus x0 to the 5. Let's do another one, C7 over C1, x minus x0 to the power of 7. So we have even terms in the series and odd terms in the polynomial series. And these things right here are numbers that we've determined before from the recurrence relationship. So y of x is equal to C0 times 1 plus C2 over C0 is minus 1/2 x minus x0 squared. C4 over C0 is 124. And this is 1 negative 720. And the C1 is x minus x0 plus C3 over C1 is minus 1/6. C5 over C1 is 1/120th. And C7 over C1 is minus 1 over 5040. Okay. And one more step. One plus minus 1 over 2 factorial plus 1 over 4 factorial plus minus 1 over 6 factorial will be x minus x0 plus minus 1 over 3 factorial. And by the way, this is 1 over 0 factorial. And this over 1 factorial. X minus x0 cubed plus 1 over 5 factorial. X minus x0 to the 5 plus minus 1 over 7 factorial, x minus x0 to the 7. All right. You remember Taylor series from undergrad school? What was the function that led to an odd to an even series with alternating signs? the cosine, right? And the one with odd alternating sign series was the sine, okay? You take the cosine, you take the derivative, evaluate it at x0, make x0 equal to 0, okay? And you get 1. If you take the derivative of that, you get the sine. Evaluate it at 0, you get 0. Take the derivative of the sine, you get the cosine. And then the derivative of that is 1. Take the derivative of the sine, you get 0. Take the derivative of that is minus the cosine, you get minus 1. So that's why the sign alternates. So this is a cosine, and this is a sine. Okay? So at x0 equals 0, we have y of x equals c0 times the cosine of x plus c1 times the sine of x. And that is the solution that we expected from the beginning. Since this is a linear, the original function, the original differential equation was a linear constant coefficient of the e that we could have solved using the auxiliary problem and ended up with, it has imaginary roots, we end up with this solution. That's what we expected. That's what we got through the series solution. Obviously, we should arrive at the same series solution. So, you can show yourself, prove that Taylor series expansion of cosine of x and sine of x are indeed the series above. Or I didn't mean to say proof, I said proof with one O on your own time. Okay? But we've done it many times. Okay? Similarly, solve, for example, the second y of x, the x squared minus y of x is equal to 0. In this case, px is equal to 0 and qx is equal to minus 1. Again, this is a constant coefficient equation, which means that we know the answer, but if we try this series solution approach, we should get to the same answer. What would be the answer of this equation? What are the roots of the auxiliary equation here? M1 and M2. A is equal to 1, B is equal to 0, C is equal to minus 1. So it's minus B plus minus B squared, 0, minus 4AC. What's the square root of 2? It's 1 divided by 2A. So it's positive 1, negative 1. Okay? If we have an equation whose auxiliary equation roots are 1 and minus 1, what is the solution? C0 times the exponential function of x plus C1 times the exponential function of minus x. Right? E to the x, e to the minus x. Which we can combine into cosine hyperbolic and sine hyperbolic, right? Let me write it here. Solution should be y of x equals to, I'm going to call it a and b, a e to the x plus b e to the minus x, not lambda, x, or y of x is equal to c cosine hyperbolic of x plus d sine hyperbolic of x. Remember what the sine and the cosine hyperbolics are? Cosine hyperbolics is e to the x plus e to the minus x divided by 2. And sine hyperbolics is e to the x minus e to the minus x divided by 2. So we can combine these two to make them cosine hyperbolic and sine hyperbolic. So either of the two is a valid solution to that equation. And we can test it again, right? We can take, let's say, the cosine hyperbolic. What is the second derivative of the cosine hyperbolic? What is the first derivative of the cosine hyperbolic? Sine hyperbolic positive. What is the first derivative of sine hyperbolic? Cosine hyperbolic positive. It never changes sign. Okay? So the second derivative of cosine hyperbolic is the cosine hyperbolic. So cosine hyperbolic minus cosine hyperbolic goes away. Same thing for the sine. Second derivative of the sine hyperbolic is the sine hyperbolic minus the sine hyperbolic. It goes away. It satisfies it. So these satisfies the equation. These satisfies the equation. These are the same with just different constants. Okay? So now we can check if the series solution approach will lead to the same answer. Try series solution about x0 equals 0 such that y of x is equal to the summation from n equals 0 to infinity of Cn x to the n. That means that the first derivative of y with respect to x is equal to the summation from n equal 1 to infinity Cn n x to the n minus 1, and the second derivative of y with respect to x squared is equal to the summation from n equal 2 to infinity of Cn n minus 1 x to the n minus 2. Same thing we did before. So plug into ODE, shift index, and relate coefficients. And we end up with Cn plus 2 over Cn is equal to 1 divided by n plus 2 n plus 1. So this is the recurrence relation. Same process that we followed last time. And now we have next page. Therefore, y of x is equal to C0 times 1 over 0 factorial plus 1 over 2 factorial times x squared plus 1 over 4 factorial times x to the 4th plus 1 over 6 factorial times x to the 6th plus C1 times 1 over 1 factorial times x plus 1 over 3 factorial times x cubed plus 1 over 5 factorial times x to the 5 plus 1 over 7 factorial times x to the 7. And that's how we collapse the whole thing using the recurrence relation so that we end up only with two constants, which is the only thing we can afford because we only have two boundary conditions, not an infinite number of ones. And therefore, y of x looks like C0 times the cosine hyperbolic of x plus C1 times the sine hyperbolic of x. So you can check for proof Taylor series expansion. So prove yourself that if you take the cosine hyperbolic and try to expand it in Taylor series, you end up with these series. If you take the sine hyperbolic, try to expand it in Taylor series, you end up with these series. And that's what we expected the solution to be. Also recall that the cosine hyperbolic of x is equal to e to the x plus e to the minus x divided by 2, while the sine hyperbolic of x is equal to e to the x minus e to the minus x divided by 2. Which means that we can take that and turn it into e to the x and e to the minus x type of solution, if we need to. So we can follow this method if, for example, the equations, the provided differential equation has real variable coefficients. The two examples that I provided have constant coefficients because we know what the answer is. So we can compare that what we're getting to the series solution is indeed the right solution. So we know what the actual solution is. Alright? So now we know that we can use this methodology, end up with a recurrence relationship, relate all the odd coefficients together, all the even coefficients together, and have a series solution. However, not all series solutions will collapse down to a known function like this. Okay? It just happens that in these two particular cases, that infinite solution for the odd terms end up being the sine, and the infinite solution for the even terms end up being the cosine, and in this one you end up being the cosine hyperbolic and the sine hyperbolic. Sometimes the solution is just basically in terms of infinite series. There's nothing you can do. It just stays there. Alright? Now, there are specific equations that have already been cataloged that have specific applications, so that the series that you end up with is an infinite series with a particular recurrence relation, has a name. Okay? And that name can be either a Bessel function, or it can be either a Legendre function, or a Legendre polynomial. Okay? It's not that they're different, it's just that there's a specific series that is called the Bessel function, or a specific infinite series that is called the Legendre function. And the reason why these are important is because these types of equations with these type of combination of functions px and qx end up showing up all the time at particular applications. And heat transfer, for example, when you do heat conduction in cylinders, you always end up with the Bessel equations. Okay? When you try to solve for the heat conduction terms in the radial direction, you end up with the Bessel equation. So you end up with a second order equation with variable coefficients that has a specific format, that you end up with specific series, that you collect and compact this series into a function called the Bessel function. Okay? It's not any type of special function, it's just a function that is called Bessel function because it's a specific combination of coefficients in an infinite series. That's it. Okay, the Legendre function happens when you try to solve heat conduction in spherical coordinate systems, or when you try to solve wave equations in the spherical coordinate system, which is very common. Because, for example, if you're solving for electromagnetic problems in space, okay, electromagnetic waves always travel in spherical coordinates, right? You have a source and they always travel spherically with respect to the point of origin. So what's going to happen when you try to solve that equation is that in one of the directions you're going to end up with an equation that looks like the Legendre equation, and then the solution to the Legendre equation are Legendre functions, which are nothing but series summations. That's it. Alright, so, for example, if Px and Qx in the second y dx squared plus Px dy dx plus Qx y of x is equal to 0 are singular, then the power series solution is only valid from the point of expansion x0 to the nearest singularity in Px and or Qx. Okay, which is a rule of Taylor series. So let's try this again with an example. If I give you this equation, 1 minus x squared, the second y dx squared, again this is a second order linear equation, 2x dy dx plus nu plus 1 y of x is equal to 0. We call this a Legendre's equation. Okay, and again, this is not arbitrary. That equation looking like that is not arbitrary. It's not that somebody said, well, let me write this equation, let me do a series solution, let me see what I get. What Legendre was trying to do was to solve an equation that showed up all the time. When people were trying to solve heat conduction problems, specifically Fourier, who was trying to solve heat conduction problems in spherical coordinate systems, he always ended up with this equation. Not in the x direction, because there's no x direction in spherical coordinates, right? It's in another direction, but the equation looks like this. So what can I do? So Legendre helped him solve it. And here's what he did. So again, this equation arises from the solution of partial differential equations PDEs in spherical coordinates. Okay? So it turns out that when we solve partial differential equations, when we have multiple dimensions, we can break them up into separate the dimensions and end up with sets of ODEs. One of the ODEs that you end up with looks like this. Okay? So if we rearrange this equation, rewriting, we get the second dy, the x squared minus 2x, 1 minus x squared, plus nu plus 1, 1 minus x squared, y of x is equal to 0. And as you can see, this is px, and this is qx. And what we notice is that px and qx are singular at x equals plus minus 1. At x equals plus minus 1. Alright? Those functions go to infinity. Which means that if we select an expansion point x0 equals 0, the solution will be only valid between minus 1 to 1, to the nearest point of singularity. Right? So the radius of convergence will be 1 of the series. Which is okay, because minus 1 and 1 might be the edge of the sphere, which is what's going to happen. And it just turns out that you can have a solution within the sphere. Alright? So you can, if you plot these two functions here, you'll notice that you have x, this is minus 1, this is plus 1, this is y, and qx looks like this, and px looks like that. But they're both singular at minus 1 and 1. So try a series expansion about x0 equals 0. Okay, you cannot expand about the singularity, okay, about x0 equals minus 1 or x0 equals plus 1, because then your radius of convergence is 0. Basically, solution is not valid anywhere. So you're going to do y of x equal to the summation from n equals 0 to infinity of cn x to the n, dy dx, n equal 1 to infinity, cn n x to the n minus 1, dx squared, n equal 2 to infinity of Cn n minus 1, x to the n minus 2. All right. So I'm going to try to skip a lot of the detail here. I have it on my notes, but we plug back into the equation. Plug back into equation. So we'll have 1 minus x squared times the second derivative, which is n equals 2 to infinity. Cn n minus 1 x to the n minus 2 minus 2x times the summation of the first derivative Cn n x to the n minus 1 plus nu times nu plus 1 times the summation from n equals 0 to infinity of Cn x to the n. All of these is equal to 0. Right? So then what we do is switching indices. Okay, you need to switch this index here to n equals 0. This index here to n equal, actually you switch this one to n equal 2 and this one to n equal 2. So of second summation and third summation. We end up with the following. 2c2 plus nu plus 1 c0 plus 6c3 plus nu plus 1 minus 2 times c1. That multiplies x plus the summation from n equal 2 to infinity of Cn plus 2 times n plus 2 n plus 1 minus Cn times n minus 1 minus 2 Cn times n plus nu plus 1 times Cn times x to the n is equal to 0. Okay? So for all of these to be 0, these needs to be 0, this needs to be 0, and these needs to be 0. So this leads to the recurrence relations. The first one that says that C2 over C0, this one is from here, is equal to minus nu plus 1 divided by 2. C3 over C1 is equal to 2 minus, this comes from here, nu plus 1 divided by 6. So this relates the first even two coefficients, the first two even coefficients, the first two odd coefficients, and then the rest are related to this recurrence relationship, which relates Cn plus 2 to Cn. So Cn plus 2 over Cn is equal to minus nu plus 1 plus n plus 1 divided by n plus 1 divided by n plus 2. So, after all that, we can use these recurrence relationships to collect a function that multiplies just C0 times 1 plus minus nu plus 1 divided by 2 factorial x squared plus minus nu plus 1 times 6 divided, or minus nu plus 1 divided by 4 factorial x to the 4th plus so on and so forth. That comes from this recurrence from the even recurrence relationship. And from the odd recurrence relationship, we have C1 times x plus 2 minus nu times nu plus 1 divided by 3 factorial x cubed plus 2 minus nu times nu plus 1 times 12 minus nu times nu plus 1 divided by 5 factorial x to the 5. Okay, so these are just, again, infinite series. Nothing ordinary about them or extraordinary about them. It's just a Legendre plotted these. He took the time, back then without computers or anything like that, to actually plot these. Y as a function of x. Okay? For it, obviously not an infinite number of terms, so but he truncated. You notice that the factorials, they grow pretty fast, right? 7 factorial is 5,040. Imagine what 13 factorial is. It's in the billions, right? So you can stop at maybe 6 or so terms. And he plotted this as a function of y. He plotted this, y as a function of x. He plotted this, y as a function of x. And he gave these functions, this series here, a name. He called it u, and this one he called v. Okay? That's it. So it's like a cosine and a sine. It's just some special functions called the Legendre function. So that was his dissertation. Plot all these by hand. I don't even want to think about how they did it, but so basically y of x is equal to C0 times u nu of x plus C1 times v nu of x, such that u nu and v nu are the Legendre functions of the first and second kind. So u is the first kind, v is the second kind of order nu, such that nu, so or if nu is an integer, if nu happens to be an integer, then these infinite series terminate. They actually truncate, not approximately, exactly truncate. That means the termination of series. And we can retrieve the so-called Legendre functions, and these are the Legendre polynomials. Pn of x and Qn of x. So that nu is equal to n. Okay? In this case, one of the polynomials, Qn, is singular, as expected, at plus minus 1, and Pn of x is well behaved. Alright, so we have these functions u and v, which are infinite series functions. It's just an infinite series that receives a name. Same way we call the cosine and the sine. They are in fact infinite series. U is an infinite series that we call the Legendre function of the first kind of order nu. It turns out that when nu is an integer, those series are no longer infinite. They terminate at a particular order. So they become Legendre polynomials because they're in fact finite degrees or finite order polynomials. Alright? So these polynomials look like this. P0 is equal to 1. P1 is equal to x. P2 is equal to 1/2 of 3x squared minus 1. P3 is equal to 1/2 of 5x cubed minus 3x. And so on and so forth, with recurrence relations, relation, n plus 1, Pn plus 1 is equal to 2n plus 1 times x times Pn, and this is, by the way, Pn of 1 of x, Pn minus n times Pn minus 1. So this is a three-way recurrence relationship where we can find out what the next order Legendre polynomial is from the previous two. And as you can see, the next order Legendre polynomial is an order higher than the previous one because it multiplies x. It's just a single order higher than the previous polynomial. Okay. These polynomials, by the way, satisfy one particular, these polynomials satisfy the orthogonality property. They're orthogonal to each other, which is something that is going to come in handy later when we solve partial differential equations, which means that the integral from minus 1 to 1 of Pm of x times Pn of x dx is equal to 0 if m is different than n, or 2 divided by 2n plus 1 if m is equal to n. This is called orthogonality. When two functions integrated over a span always yield 0 except when the order of the two functions is the same. Okay, sines and cosines are also orthogonal. In this case, these polynomials are also orthogonal. And that's a very powerful property because, as you will see, that's after exam number 2, it will be the only way we can actually determine the unknown coefficients in infinite CL, okay, in partial differential equations. Okay, but let's not worry about that just yet. That's P and Q. Q0 is equal to 1/2. We said that Q was a singular function. 1 plus x, 1 minus x. But it's definitely singular at x equal 1 and at x equal to minus 1, as expected. Q1 is equal to x over 2 log of 1 plus x, 1 minus x, minus 1. Q2 is equal to 3x squared minus 1 divided by 4 log of 1 plus x, 1 minus x, minus 3x divided by 2 plus a whole bunch of other things, which you can determine through also a recurrence relationship. And these, as you can see, are singular at x equals plus minus 1. All of these. So, the final solution of the Legendre's equation is y of x is equal to C0 times u nu of x plus C1 of v nu of x. That is, if nu is not an integer, or y of x is equal to C0 times Pn of x plus C1 times Qn of x if nu is equal to n, which is equal to an integer. And just like sines and cosines, it's just functions that received a different name. All right. Again, this is not arbitrary. The reason why we're learning Legendre's equation is because Legendre equation shows up all the time when you're solving equations in spherical coordinate systems. Okay? Now, when you're solving equations in cylindrical coordinate systems, which is very important for us engineers because we deal with pipes all the time, we get Bessel equations, which is an equation that looks a little bit different. And in order to solve the Bessel equation, we're going to follow a similar approach of expanding an infinite series. With the difference is we're going to use a slightly different methodology called the Frobenius method, in which we actually expand about the singularity, okay, and try to avoid it by regularizing the equation in a special way. And we end up, as you expect, the solution of the Bessel equation are the Bessel functions, the first and second kind of a particular order. Okay, and those functions are tabulated. Bessel was an astrophysicist, actually from this century, no, from the 20th century, and he developed those functions because he was working on telescopes. Okay, and as telescopes are cylindrical, he ended up with those equations for the optical characteristics of the telescopes. So the Bessel equations, actually part of his dissertation was to derive the Bessel equations, come up with the Bessel functions, and tabulate, plot the Bessel functions, again, one by one, for different values of x, infinite series, truncated, obviously, because you have decreasing coefficients because of the factorials in the denominator. All right, so this is it for today, and as I said, when we get back on Thursday, we'll talk about Bessel equations. All right, any questions?
Freaking awesome.